and the outside is 4. This is 1, 2, 3, and the outside is 4. But they have different properties. They are different planar embeddings. And actually, one way to see that is if we construct their dual graphs. Okay. And yeah, so let's just do it. So it helps to use a different color. So what I now do is I place a dot in every region, and there are 4 regions. And over here there are 4 regions. 1, 2. This is another day I'm sad that Gabe's not here because he's been obsessing over this forever. And now I will connect the dots if the 2 regions are adjacent. Okay, are these 2 regions adjacent?
Yeah.
None of them come in here though.
I think they're like not.
No?
Yeah, I say no. No.
Okay.
Because they don't share an edge. Right? 2 regions are adjacent if they share an edge, and those 2 don't. But these 2 share an edge, so we connect them. These 2 share an edge, so we connect them. This region shares an edge with the outside region, so we connect. What else?
And then the weird
A lot of them share
with the outside.
these 2 regions share a thing.
That's like it.
Is that it?
That's it.
No, I feel like there's more.
There's a loop with itself. The one on the far left shares an edge with itself.
One on the far left shares an edge with itself. Oh, yes. He says that this edge is the edge between the outside region and itself. So this is a this.
That's so if there's just like a line.
And that's it. I feel like there's like way more. No. 1, 2. Oh, and no, there's another. That's right, because you got to do it with every edge. Sorry, totally screwed this up. So it's not whether they share or not, it's by how many edges they share. So for example, this region shares, we drew this edge because they have this edge in common. But they also have this edge in common. So I need another, I guess I should go out the edge that they,
Yeah.
and they also share that edge.
Yeah.
So I need to do that. And then also these two regions share that edge. So there's like another one.
Yeah. Yeah, good.
Now, have I done this correctly? Is there a line through every?
Yes.
And I might even need 2. No, that looks good.
No, that's
Who's happy? Looks crazy. Okay, let's do the other one. Here, again, we do it. These 2 are connected, check. These 2 are connected, check.
by like 3 things.
But they're also connected another time, being,
Up through the top and up through the right.
and also that.
Yeah, and it has a loop with itself.
And also this edge, the outside
Yeah, the outside thing has a loop. Yeah.
connects to itself via that edge.
The one on the left.
In fact, if we're sticking with the notation, we should possibly do it like that. Because that shows the loop cutting through that edge. That sort of explains why. Do you see kind of how I did that? Because right, every edge generates a... Alright, if you're not understanding what's going on, you should speak up. And then, let's see, the outside also shares an edge with this region, through that, and it also through that edge. And what edge haven't I covered yet?
The one on
The
the
loop.
Yeah.
How the hell does that work?
It connects to the one on the outside.
It is connected to the outside. True. And
Draw a
so
line from that one.
I have to go like that.
Yeah.
Okay. So I think if a graph is planar, its dual is also planar. I'm just conjecturing that right now. That
Also,
seems
it's
the
the same thing
Yo.
as like dual for planar.
It is the dual thing. In fact, question?
Can you change the loop on the left one so that it matches?
Yeah,
the
just to make it to be consistent, right?
It's
between those.
So I need to go like zoom like that. Is that what you meant, Jason?
True, because now in each thing there's like that's where the picks is like another.
Something like that. Okay, so this is the sense of a graph and its dual. And by the way, while we're on the subject, there are like these brilliant facts about the Platonic solids. For example, let's draw the dual of the cube. Okay, what is the planar embedding of a cube? This is one of the ones I've mastered.
Is the dual the octahedron?
Some crap like that, yeah. because we kind of saw that already happening like over there, right? Because there's this relationship. So here's the cube, right?
Yeah.
It has 6 faces. What are they? Well, I'll draw. Is this all getting on the camera? Just drawing all these pretty pictures. It's like discrete math. Finally. All right. So here are all the regions. 1 dot for each region. Let's draw an edge between every 2 which are connected. So bosom, 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 and then they're each connected to this one, right?
Only the, like,
Or
those
except for the
4.
middle one.
Just the outside.
Yeah.
Okay. Recognize this purple monstrosity?
Oh, another cube.
I can see it.
It is it actually just is the octahedron,
Wait, what?
I think. I don't see it, to be honest. I'm just using my knowledge.
Like the top of the base
Okay, how do you see it? I don't.
It's like looking straight.
Oh yeah. Because watch, I'll label these. This 1, 2, 3, 4, 5, 6.
Yeah, that's
So watch this crap. That's 1. That's 2. That's 3. Zonk, zonk, zonk. And then 4, 5, 6 are like in the middle. Yeah. And 4, 5, and 6 are connected. And then 4 is connected to 1 and 2. Check, check. 5 is connected to 1 and 3. Boom, boom, boom.
That's like very.
Okay. Yeah. So the cube, and of course, this is like this relationship is like symmetrical, right? The dual of the octahedron is the cube.
That's so.
Actually, so anytime you Google like some kind of weird shape, it'll start rambling on about what the dual of that shape is, and it's actually like a whole fascinating world of that. Also, by the way, this is not a shock over here because we saw that there's like this inverse relationship between all these things. I'm not going to go back into this. But yes, it is true that the dual of the dodecahedron is the icosahedron. The dual of the tetrahedron is itself. Yep.
That's weird.
Whoa. Okay. So, we're learning about graphs. We're learning about the duals of graphs. Now let's do a little bit of chromatic numbering. Suppose I give you a particular graph and you tell me what the chromatic number is. Okay, I'm just going to do the example from the book like really fast. Okay, take this graph. What is the chromatic number of this graph? Okay, Rami doesn't even need to think. She just rummies up the answer immediately. What's your answer?
3, right?
3. Yeah, you're right. Because we could, for example, color this red. We could, for example, color this purple. We could color this blue. But as this graph actually has 2 independent components, then just like duh, right? I could just repeat those. So in fact, like the chromatic number of a graph has to be greater than or equal to like the chromatic number of one of its components or some crap like that, right? Or rephrase that in the appropriate way.
That's like true.
Restate the sentence until it's like correct. Okay, good. So the chromatic number of this graph is 3. We have a symbol for this, we call it chi. We do the chi. How do I draw chi? It's like an X, but it's like a fancy. It's like a cha. So the chromatic number of a graph is the smallest. Does everyone get it? Say yes.
Yes.
Okay, so I'm going to erase that backboard also, even though it's so beautiful. And we will now prove the 4-color theorem. Haha, just kidding. That can't be done. In fact, the reason why the 4-color theorem is so famous is because when about 100 years went by, and no one could prove it, Eventually, in the 70s, they said, all right, let's break it down into 2,000 different cases.
Oh my god.
And these 2,000 different cases are very, very difficult to check. So in fact, we're going to solve it with a computer. And they wrote a computer program. This was back when like the average American had never seen a computer before or even knew what it was. And the computer program checked all the cases, and they published the proof as like, we're done. we showed that that every map can be colored 4 colors. This freaked people out. Okay, you guys don't know Waldstein now because he left and retired. But who remembers him from like 9th grade? Like, you know, he was just a screaming crazy guy. Yoni had him. So one of the things about him, I mean, there's hundreds of things to say about him, but he's a crazy screaming guy. He was really old. Bless you. He hated the internet, and he had a fascination with everything that was on. He had if it was on the internet, it was bad. If it wasn't on the internet, it was good. And so what would happen is he would be teaching things in class, and someone would be like, "Oh, I already know that proof. I already know that." And he'd be like, "What? Did you learn that on the internet?" Just like, if you learned on the internet, he would immediately reject you. If you'd happen to read it in a book, that was okay. But if you saw it on the internet, bad. Alright, so this was roughly the state of mathematicians in the 1970s. They said, "What? You're going to prove it with a computer? What is it? Are you crazy?" And so there were a lot of people who perhaps they had a little bit more sophisticated objections, but they had philosophical objections to the very idea that a mathematical theorem, an important one, should be just proven by just an exhaustive list of cases, which are too impossible for any one person to check. And this does get into some interesting questions of like, algorithm verification, and to what extent must we prove that the algorithm works, and how do those proofs go, and like blah 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 blah. So I guess according to the book they reduced the number of cases, but still there does not exist a simple, elegant proof of the 4-color theorem that you can just read in like one paper, then you can just understand.
We also, fun fact, the name of the
Fun
computer
fact.
program that helped is called COQ.
Oh yeah, COQ, yeah, which I think is like, maybe like a Dutch word for, can you look up where that's called? No, it's probably an acronym, but I think also, I don't remember. Okay, that's only one of the many things that happen in the Magnet program. Like we have a whole class called Anal on your transcript. That is, you get Duval and Schaefer in a room together and they can laugh about that over and over and over and over again. All right, now we get to the grand theorem of today. Guess what we are going to do, Ethan Holland? We are going to prove the 5-color theorem. That's not the 4-color theorem, but it's pretty good. The nice thing about the 5-color theorem is I can do it in 20 minutes. First, are you ready?
Yeah.
We will now prove the 5-color theorem, which is also pretty hard. Okay. The 5-color theorem says, wait, I think I need my notes. Or I need like a book or something. Or I need that thing. Can you pass that thing over there on the fish? Just like pass that back to the room. Okay, the 5-color theorem says, the 5-color theorem says every graph can be colored with just 5 colors. And really what it says is that the chromatic number of a planar graph, the chromatic number of a planar graph is at most 5. Okay. The chromatic number of a planar graph is at most 5. Okay, so this is a little bit hard. And what we are going to do is for this we are first going to prove a lemma. Okay, so first a lemma. Let's go over here. Where do I want the lemma? Maybe here. Okay. There is a lemma. And the lemma, move the camera please, is that in any planar graph, okay, now everyone, and too lazy to write this down, but just planar graphs are ones in which none of the edges cross each other, right? So loosely speaking, if you have a planar graph, there are like not so many edges, okay? Because if there are like many, many, many edges, then it just can't be planar. For example, a complete graph cannot be planar, although I haven't proved that. All right, well, the lemma says every connected planar simple graph has a vertex with degree less than or equal to 5. Okay. Every connected, every connected
Don't have to. 4 is fine.
planar simple graph has a vertex with degree less than or equal to 5. Okay.
Wait, just one?
At least one. Has at least one vertex with degree less than or equal to 5. No, you could have a planar graph with a vertex with a very high degree. For example, the star graph is planar.
Never mind, got it.
Got it, right?
Yeah.
So it doesn't say that all the vertices have low degree. It says somewhere in a planar graph there must be a vertex of low degree. Because if all the vertices have high degree, then you have a lot of edges. And if you have way too many edges, there's no way for the graph to be planar. Who's with me? Okay. All right. Well, this lemma is going to be dependent on another lemma. The nice thing is that this other lemma was homework problem number 1. So for the plurality of you who did your homework, or something, let's go over number 1 from the homework. Number 1 from the homework is called proposition 10.5. If you did any of the homework, presumably you've tried at least number 1. And what does number 1 say? Number 1 says, number 1 walks you through a proof of the following fact. If a connected planar simple graph, if a connected planar simple graph has epsilon edges and n greater than or equal to 3 vertices, then epsilon is less than or equal to 3n minus 6. Okay. First of all, the graph is connected. Second of all, it's planar. Third of all, it's simple. If there are a certain number of edges, what this basically says is you can't have too many edges. Perhaps, are you with me?
What? Yeah.
Okay. If you have a bunch of vertices, then there is an upper bound on the number of edges you can have, with it still being planar, which, as we've been talking about, makes sense that there should be an upper bound on the number of edges. This is the upper bound. Okay. How do you do this proof? They walk you through it by introducing the concept of a region. And a region, I think I need the book.
Wait, do you really care if it's connected?
I don't. If it is
I don't think it matters.
disconnected, then it's like even easier to prove, right?
Yeah.
Right.
So,
So
that's
let's
not,
just say
like,
it's connected.
unnecessary.
Am I going to use that it's connected? I might.
No, but I'm saying if it's true for connected graphs, it has to be true.
Yes, I agree. Okay, so what they do is they define this concept of the degree of a region. So what is the degree of a region? The degree of a region is kind of what we were talking about over there-ish, right? It's the number of edges in the region. Is the number of edges bounding the region. Bounding the region. So, for example, imagine we had a simple graph that looked like this. This graph has 3 regions. What are the degrees of these 3 regions? Well, the degree of this region would be 4, because it has 4 bounding edges. Here would be 3, and here would be the outside region, 5, because it has 5 things. Okay. And then there's some crap about like loops and stuff like that, but who cares?
You can make an isomorphic graph that has different regions.
You can make an isomorphic graph
So
which
this
has
is-
different regions.
this is
Yes.
only for
Rami is
one
saying something important, which is
particular planar
just because two graphs are isomorphic does not mean they share. This is one of the properties that they do not necessarily share, right? So what we should really refer to is the particular planar embedding of a graph, I guess. Well, yes. Once I have the graph. Anyway, can we move on? Okay, good. All right. Okay. So part B of the homework, part A of the homework just drew this weird little picture and said, yo, first of all it said, what should the degree of a loop be? So I didn't have an answer to this. I thought it was just 1.
Yeah.
But it turns out it might be 2. But
They mentioned it.
are you sure? I know that the degree of that vertex is 2, but the degree of the region? They just asked. There was no answer.
No, it's because of the.
Well,
I feel like it should be 1, but I'm not totally
What
sure.
does this mean? What's the benchmark?
An edge terminating in a degree 1 vertex will be, but this has vertex at degree 2. So I think that this is 1, but it turns out I don't care, because my whole theorem is going to be about simple graphs, so I'm not interested in loops. And then it said something else, which is, what is the degree of a region between two edges that have the same pair of vertices? So it drew this picture in the book, and it said, what is the degree of this region? And this would just be 2, I think, right? Yeah, so I didn't understand that. But one thing that's important is that if you suddenly do this, if I suddenly add a little doop, then yes, says Ari, it is built into the definition of the degree of a region that an edge which terminates in a vertex of degree 1 counts twice. So in fact, this outside region would be have degree 7. 1, 2, 3, 4, 5, 6, 7. Do you guys all see that?
Because it has to add up to it.
Because 1, 2, 3, 4, 5, and then 6, 7. I think of the degree of a region as how many ways you can leave that region, sort of, right? So this little square I can leave through 4 different doors. This region I can leave in 7 ways. That way, that way, that way, that way, that way. And then I step into here. Who knows where I end up? It turns out I end up back in the same region, but I didn't know that yet, right? So it's like how many doors out? I can leave through that door, somewhere inside of it. Okay. Wait, we gotta go really fast. We're inside of a lemma, Part B says, what is the lower bound on the degree of a region in a connected planar simple graph with n greater than or equal to 3? Well, if I have at least 3 vertices, then my situation might look like this, or it might look like this, say, right? If it looks like this, what's the degree of this region? 3. And what's the degree of this region? 3. If it looks like this, what's the degree of this one?
4.
There's only one region and it has degree 4. Because I can leave, or leave. Okay, so I claim that the minimum degree is 3. Do you agree?
Edge.
Okay, so the degree of any region has to be greater than or equal to 3. Let's call that a fact. That is the
Simple and connected.
in a simple, planar, connected, all that stuff. Okay, good. Next, part C said, prove that the sum of the degrees of the region is twice the number of edges. Well, part C says, what is the sum of the degrees of all the regions? That's just going to be twice the number of edges. I feel like that's just
Handshake.
That's just is it handshake? Yeah. Right, why is that true again? Because take any region, if you add up all the degrees, oh yeah. If you add up the degrees of all the regions, you're just counting every edge twice. It's a version of handshake. It's not exactly a handshake, but it's a handshake-like theorem. Do I need to go into more details about that? It just comes straight from the definition. Jason, we good? Everyone please stay focused. That's part C. Part D says combine parts B and C to show that if there are rho regions, then rho is less than 2 pi over 3. Well, 2 pi over 2 e over 3, not pi, sorry. So the sum of the degrees of the regions has to be, oh, okay, so the sums of the degrees of all the regions has to be, as the degree of each region has to be greater than or equal to 3, right? If each region has degree greater than or equal to 3, then if I add up all the degrees of all the regions, I'm going to get 3 times the number of regions. That's very easy. Do you want me to say it one more time? No? Benda says no. Who is with me? Noah, you're doing that sleepy thing again. No, thumbs down, Noah. Thumbs down. Okay, good. And of course, what is the sum of the degrees of all the regions? It's 2 epsilon. So 2 epsilon is greater than or equal to 3 rho, and that shows that rho is less than or equal to 2 epsilon over 3.
Yeah.
Okay, good. So that was the homework problem. Then the last thing you had to do was part E. And part E for this one homework problem said, use Euler's formula to complete the proof of the proposition. What does Euler's formula say? Euler's formula says that rho is the number of edges minus the number of vertices plus 2. So I know that rho has to be less than or equal to 2 epsilon over 3. So that means that epsilon minus n plus 2 has to be less than or equal to 2 epsilon over 3. And if I now just do a little bit of algebra 1, if I multiply through by 3, I get 3 epsilon minus 3n plus 6 is less than or equal to 2 epsilon. And am I done? I think I'm done. Epsilon is less than or equal to 3n minus 6. There.
Yeah.
Okay. So this theorem, proposition 10.5 proven. If I have a connected planar simple graph, then there is an upper bound on the number of edges. Okay. Well, who is with me? Say everyone.
Everyone.
Everyone! Good! Okay, now we get back to the lemma. The lemma says every connected planar simple graph has at least one vertex with degree less than or equal to 5. Well, if n is less than or equal to 6, then this is trivial.
Yeah.
Because if I only have 6 vertices or fewer, then no vertex can have degree greater than 5.
Yeah.
Okay. So, duh. Okay, so let's suppose, so in order to do a proof by contradiction, I want to prove this theorem, right? So suppose that n is bigger than 6. In other words, suppose I have a graph with a high degree, or a high number of vertices, and the degree of each vertex is greater than or equal to 6. Right? Because that's the opposite of saying that there is one vertex with degree less than or equal to 5, is to say that all the vertices have degree greater than or equal to 6. Well then, how many edges are there?
Like,
By the handshake, how many edges would there be?
well,
By handshake, twice, if you multiply every edge count, the sum of the degrees of all the vertices is just 2 times the number of edges. That's literally the handshake.
yeah.
But if the degree of every vertex is greater than or equal to 6, then what is the sum of all of these?
It's like at least.
So
It depends on n. It's like a function of n, but then there you have epsilon is another function of n, and they're just like it's gonna lead to a contradiction.
yeah, wait, hold on. I think it's even simpler than that, right? If the degree of every single vertex is greater than or equal to 6, and if I so by handshake this is true. Maybe I'll like put that in a box. So if the degree of every vertex is greater than or equal to 6, then the sums of the degrees of all the vertices has to be greater than or equal to
N times 6.
n times 6.
Yeah. And
Right?
then
Because if every vertex has degree greater than 6 and there are n vertices, then the sum of all of them.
so
So that
n
means
that
that
the edges
2
are-
epsilon is greater than or equal to 6n.
Which means that epsilon is greater than or equal to 3n, but
Which
it's also
means,
smaller than.
wait,
Yeah.
something went wrong.
No, that's
No.
That's fine.
That's
Epsilon
Oh
is
yeah,
greater
which
than
means that
3n,
epsilon is
also
greater
smaller
than or equal to 3n.
and it's
But,
also smaller than
contradiction.
3n minus 6. So,
Contradiction, right?
yeah.
Okay, so by imagining that all the vertices have high degree and using the handshake, I determine that there must be greater than or equal to 3n edges, but there can't be, because I already showed in proposition 10.5 that there's an upper bound on the number of edges. Who's with me?
Yes.
That was a contradiction. Okay, all of that was just so we could get started. And now we're going to finish this off. No one's leaving this room. Lock the doors. Code red. Okay. So, Benda, we got 10 minutes. I am going to prove the 5-color theorem.
We have 10 minutes, that was like 6.
No, it's 10.
9.
Uh,
You have to think it's 6.
the 5-color theorem says the chromatic number of a planar graph is at most 5. Okay. Well, here is what we are going to do. We are going to do it by induction. So use complete induction. Base case is if the graph has n less than or equal to 5 vertices. So base case, n is less than or equal to 5 vertices. Okay, well, can I just say, duh, if there are only 5 vertices, then of course I can color the graph with 5 colors. Just color them all, each one a different color. Say good.
Good.
Okay, good. All right, now the inductive hypothesis. And my inductive hypothesis is going to be that all graphs with n vertices, so all graphs with n vertices have chromatic number, have a chi of 5 or less. In other words, let's imagine that every graph can be colored with 5 colors of a certain number of vertices. And then what I need to prove is that an arbitrary graph G, G with n plus 1 vertices has a chromatic number less than or equal to 5. Follow? Okay, so I'm going to do this. So here's what we do. Take a graph G. And now what we are going to do is we're going to use our lemma, right? Our graph G must have a vertex of degree less than or equal to 5. Call that vertex V. So G must have a vertex V with degree less than or equal to 5 by the lemma. Okay, so we're going to start everything on the one vertex that we know to be of low degree, relatively low degree. Okay, and there are a couple of cases. Case 1 is that the degree of V is actually less than 5. Okay, well, I don't have time to write this all out, so just listen to me. If the degree of the if we are guaranteed that there's a vertex with degree less than 5 or equal to 5. Imagine it has degree 4. Okay? If that vertex has degree 4, then take out that vertex temporarily. You take out that vertex, what remains? What remains is a lot more graph, but it's a graph with n minus, or it's a graph with n vertices. Right, it's a graph with n vertices. And what do we know about every graph with n vertices? It has chromatic number less than or equal to 5. So look, if this whole graph can be colored with less than or equal to 5, then simply go to this vertex and color it with the 5th color, right? Because if this vertex, if it only has 4 neighbors, then this is a trivial inductive step. Because let's say, at worst, that its 4 neighbors are colored with 4 different colors. Who's with me?
Yeah.
If its neighbors are colored with 4 different colors, then just, dude, color this one with the 5th color. Done.
Wait, what are you doing the induction on?
I'm doing the induction on all graphs with degree n plus 1.
Yeah, but like, this
N
is
plus
kind of going backwards.
1. So what I'm arguing is that if on the assumption that every graph of degree n is colorable with 5 colors,